So we're going to do a quick example here for playing around with the power and sample size calculators. This is going to use the TIDA paper as a reference to plan a new study. So if we want to plan a new study to further address hypertension in pregnant women, based on the results from TIDA et al. In Table 3, we're going to have the treatment arm with severe hypertension of 36.1 and a systolic blood pressure of 129.5 with a standard deviation of 10. So if you take a look at the TIDA paper, these results are coming from Table 3. So you have the systolic BP, this is our continuous outcome, and this is the active treatment of 129.5, standard deviation of 10. And you look at severe hypertension with a percentage of severe hypertension of 36%. So that would be our reference. So we're going to take this as being effective and now looking to plan a new study, and this would become our new comparator group versus a newer intervention. So in looking at this example, let's talk about finding N. What would be the sample size needed to determine if the new intervention has a 26% severe hypertension rate? So the TIDA group determined a 36% severe hypertension rate. What would happen if we had a new intervention, whether it be a new drug or the intervention that they use, plus now adding in maybe a lifestyle change to see if we could get to 26% severe hypertension, so an absolute 10% change. Again, using 1-to-1 matching with a control group that has an expected success rate of 36%. So assuming an alpha of 0.05 and 80% power, what would our sample size be needed in this very first row? So 36% in what would be our control group and 26% in our new intervention group. So I'm simply going to go to powerandsamplesize.com, go straight to the calculator, and what we would want here would be comparing two proportions for two-sample, two-sided equality. And we want to know what our sample size is here. So if you go back here, we're looking for the N needed. And we want to determine sample size, 80% power, alpha of 0.05. Our group A proportion is 0.36. And our group B proportion is 0.26. And we're doing a 1-to-1 sampling ratio here. So our group A proportion is our standard proportion. So the 0.36 that TIDA found in their new treatment becomes our control group. And our new group is group B, 0.26. 80% power, 5% alpha, sampling ratio 1-to-1, and we're trying to determine sample size. So I'm simply going to press calculate. This gives us an N of 332 in group B. So it's really important here on sample size that you notice it's N subgroup B. That means it's half the sample size. So we would need NB and NA. So 332 times 2, 332 times 2, 466, 664, 664 people. So we would need 664 people here total, 332 per group, to detect that difference using these estimates. Now, if we want to increase our power to 90%, we're going to go about this a little bit differently. So now let's say we want to increase our power to 90%, change your power to 90%, and recalculate. Now you can see we need 444 people, 444 people per group, which makes it 888. Okay, so the next question is what if our estimates are up or down by 5% in each group, so allowing for a little wiggle room? So let's say that the standard treatment, now that we know better from the TIDA group how to do this intervention, let's say it actually goes down to 31%, but we still think our new treatment group is 26%. This means it's going to be harder to tell these apart, right? They're closer together. So instead of 36 and 26, we've got 31 and 26. It's going to be more difficult to tell them apart, which means I can expect that we'll need more people. So back to my calculator, I'm going to change my power back to 80%, and I'm going to change my group A proportion to 0.31, and we should expect our sample size to go up here. Press calculate, and it goes way up to 1,273 per group. 1,273 per group is 2,546 that we would need total. 2,546 that we would need per total to tell that small of a difference in severe hypertension if we were off by 5% in our standard treatment. So if our standard treatment group performed really, really well. So you can tell here on this group that if our standard treatment went down to 31 and our new treatment went up to 31, we would never be able to tell this different, right? They're the same. So we're not even going to look at that. In the other scenario, if our standard treatment stayed at 36% and our new treatment goes up to 31, we're still looking at a 5% difference. So let's put this back up at 0.36, and we're going to put this at 0.31, and we're going to calculate. And what you'll notice is that it shifted ever so slightly to 1393. 1393 doubled again is 2786. And you might ask yourself, if it's an absolute 5% difference, why aren't these two numbers the same? And that's because power is not linear. So you've changed the reference point, and the closer that you get to 0, right, these are closer to 0, they're on the smaller end, you see a difference in change versus these, right? So these are closer together. You just need to be really mindful that when you change power, you don't actually get a linear change when you change your percentages or when you change your continuous. So that's how you would do finding your N. Okay, so now let's go ahead and say that the researcher tells you that they can only afford 20%, or excuse me, only afford 20 subjects. And they expect that the new group will have a rate of 25%. And they're going to use the standard of care. So they're not going to use this new standard treatment that Tita et al. Did. They're actually going to use the standard of care treatment arm. So let's say there's in a place where they're not going to be able to implement what Tita et al. Found. They're going to use standard of care, just whatever the doctor had originally prescribed to maintain blood pressure. So that had an event rate of 25%. So if you go back here to table 3 for severe hypertension, and you say that it was 44%, and now we think we're going to have a new intervention that is 25%, and they're going to compare it to 44% rate applies. So now they have 25% in the new, 44% is standard of care, and they have an alpha of 0.05, and they want to do a power pilot study at 70%. Can they detect that difference with 20 people? So this is a little bit of a different take here. I'm actually going to go back out and reset this. So 2 sample 2 equality, 2 sample 2 equality, and I'm going to look for power because I know my sample size is fixed. My sample size is fixed at 20 total subjects for this study, which means 10 per arm. 20 total subjects, 10 per arm, and I want to see what the power is with 44% here and my new group being 25%, 1-to-1, and I'm going to calculate. Ooh, goodness gracious, my power is 15%. So this is a really small sample size with 20 total subjects. Even with as big of a difference this is I have very little power. So the answer is no. Only 15% power to detect this difference with 20 total participants, 10 per group. Okay, so what kind of difference can they detect from 44% with this number of people? So if they can really only stay at 10 per group, now I'm going to start going down, right? So if we know that 44 is held solid, let's see if what 20% gets me. Well, 22% power. Let's take a big leap and go to 10%. Ooh, we're still not even at a coin toss here. Okay, what about 5%? So this would be a super effective intervention. Nearly nobody with severe hypertension. And we're still only at 62% power. So that's a really low amount of power with a very unlikely outcome. Only 5% of people in this new intervention having severe hypertension. And remember, in the TITA paper, we were still at 36% hypertension, and that was an effective outcome. So you would have to go back to this investigator and say, you can't, even here, even with 5% severe hypertension in new treatment, only 62% power. So they're going to need to increase their sample size, right? So if you wanted to sort of go above and beyond, you could potentially go back to them and say, okay, now my power is 70%, and we think we've got 44 and 25, which is what they think that they were going to have. And now tell me what my sample size is. Oh, I need to go back and reset here. So I'm going to change my power to 70%. And group A is at 45. And I think this is going to be 25. Is that right? 44% and 25. So let's go back here and do 44% and 25. So I would need 75 people per group. And so you could tell them if they're stuck on these that you would need 77 per group. Or 154 total for 70% power with these estimates, and see if they could cut costs somewhere. Okay, so now going into continuous outcomes, thinking about these SBP measures with the new treatment, coming again from table 3 on TITA. So going back here to table 3, we see that the mean systolic blood pressure during those prenatal visits was 129.5 with a standard deviation of 10. We can see actually over here as well that there was a standard deviation of 10 in the standard treatment, so we're pretty comfortable with an SD of 10. Doing a new intervention, they think it's going to reduce the systolic blood pressure another 8, so an absolute 8, keeping with that standard deviation of 10. So if we're going to do a two-sided t-test, an alpha of 0.05, how many participants would it take to get 80% power? So we've got 129, and we think it's going to reduce it 8. This is actually be 121. So we're going to hold those changes steady. I'm not going to change those, and we're just going to play around with standard deviation. So going back to powerandsamplesize.com, we're going to go back up to two means, two-sided equality. And it's going to do a similar thing here. It's going to do a similar thing here. Now we are looking for the N needed and we've got our power fixed at 80%, sample size, or to alpha of 0.05. The group A mean we think is 129. The group B mean is 121. The default standard deviation was 10, so that's fine, and our sampling ratio is 1 to 1. So we're going to calculate. Well, that's pretty good. Only 25 per group to tell a difference of 8 apart on a continuous endpoint. So 25 per group, so we need a 50 total. So 50 total to see if we can get a reduction of 8 with a standard deviation of 10. Now, what happens if our standard deviation was really underestimated here and our standard deviation estimate's actually a 15? So let's recalculate that. Oh boy, we go up to 56 per group. So that's now 112 that we would need. Our linear logic would dictate that if we went up by this much from here to here, we'd go up by that same amount here to there. And let's just check this out here and go up to 20 and press calculate. And now we've gone up to 98 per group, up to a total of 196. So our difference from here to here, from the 112 to the 50, was a difference of 62. And our difference from the 20 to the 15 was a difference of 84. So again, you can see here that power is not linear. Misestimating or underestimating your standard deviation on continuous endpoints is the biggest single killer of studies. So you always want to overestimate your standard deviation. So even though we were relatively secure on the standard deviation estimate here, if you were planning a new study, you'd almost always want to plan for a standard deviation of 1.5 times as high, or at least a 15 standard deviation here. Now, of course, you could take a look at smaller differences or bigger differences if SBP was your outcome here. You always need fewer people for continuous metrics than you do for categorical metrics. And the reason for that is your standard deviation is based on your proportion for categorical, so those are not independent, whereas you have independent metrics for your continuous measures. So there's more on that that you'll learn if you take a power and sample size class. But for now, that's how you play around with those. I will make an announcement about what to do for non-parametrics. The power and sample size Vanderbilt program will do the Wilcoxon and the Fisher's exact. Powerandsamplesize.com will not, but there's a quick and easy way to make that adjustment, and I will post that in an announcement.